Welcome to Learn Extra Teacher Talk. My name is John, and today we are focusing on the teaching of mathematics. And in particular, we're going to start a discussion on the teaching of Euclidean geometry. Now, Euclidean geometry hasn't been part of the core maths curriculum for a little while. But if we look at the CAPS document, we know that Euclidean geometry plays a special part of the grade 10 curriculum, and it will build into the formal assessment in grade 11 and grade 12 for all learners taking mathematics. So that's what we want to start the discussion on. How are we going to do this? What are the reasons for it? And try and give some suggestions about approaches that one could be taking in the teaching of Euclidean geometry. But before we get into that, let's just go quickly to the schedule. Remember, Learn Extra is here for learners and teachers in the process we're wanting to support what's happening in classrooms. And so the schedule follows the laid out pace setters and documents in the CAPS document, and those are the topics that we're dealing with at the moment. So let's have a look at it. Coming up directly after this, we're going to be focusing in grade 10 at 4 o'clock, and then at 5 o'clock we're going on to grade 11, and at 6 o'clock we're dealing with the topics for grade 12. So that's the one thing. Then during the weekend, we also are doing a revision series for grade 12 on a Saturday between 9 o'clock and 10:30. That's the time for mathematics. We repeat the weekday live session from 3 o'clock until 4 o'clock. And then on Sunday, we're alternating between grade 10 and 11, and we're going to be looking at the same time slot for mathematics, 9 until 10:30 on Sunday, and a repeat of the live broadcast from 3 until 4. Now, this program, this initiative of Learn Extra is really about giving the opportunity to learners and teachers to talk to each other, to talk to us, so that we can make sure that your queries and your learning difficulties are sorted out, and that we can play a role in helping you get along. So we want some interaction, and the way that we interact is 3 ways at the moment. The phone number to dial is 086 1058 262. During live broadcasts, there's somebody watching that phone and you'll be able to talk to them. Otherwise, you're going to have to leave a message and leave your contact details. If possible, leave an email address. We'd really appreciate that. It just helps us get back to more people. The email, if you've got a query or your learners have a query and they're wanting to know something, give us the background to it. Our help desk is manned by different teachers, and we would love to respond to that. It's not a homework service, but if you have a question about Learn Extra, about doing a particular question, and you're stuck at a particular point, or you're not sure how to teach or to approach a particular section, then use the help desk. Encourage your learners to use the help desk as well, and we'll formally respond to that. Then Facebook is the third medium, and it's facebook.com/Learn Extra. This is interactive. This is what's happening on the while the show is being broadcast, and we're finding that learners are helping each other out. And that's what we would encourage you to do. Tell your learners about it. We've had some great success. Following is building. There are more and more learners doing that. During last week, we celebrated the fact that there were 10,000 learners that had gone to the Facebook page and indicated that they were enjoying and liking that particular page. Now, we'd like to invite you as teachers to get on to Learn Extra Teacher Talk. So another Facebook page where we're posting different types of content that is specifically aimed at teaching, and we'd like to hear your comments on that page as well. So please interact with us. We'd love to hear from you. Just a very brief thing in terms of what else is available. If we have a look at here, you can see the Learn Extra page, and you can see that we're up to 10,224 people that have gone to the page at various stages. The Learn Extra Teacher Talk page looks like that, and we're continuing to build that one. And then the next one that I wanted to just remind you about is that if you've perhaps missed a session of Teacher Talk, then go to YouTube, the YouTube channel. It's YouTube and then /mindset learn, and you'll be able to find our page. Search amongst that and you'll find Teacher Talk is one of the things you can search for. You'll find the shows, you can watch them on a computer or download them, and I'm sure that will be helpful to you. Now, we're going to go to a short break now. Directly after the break, we're going to get into talking about Euclidean geometry, the teaching of Euclidean geometry. What we're going to do is we're going to take a look at a checklist. What's the content required? We're going to say, why should we teach Euclidean geometry? Take a look at some approaches to teaching Euclidean geometry, and then look at resources for teaching geometry. So please join me after this, and we'll be looking at various things and chatting about these topics. See you just now. Welcome back, colleagues. This is Learn Extra Teacher Talk. My name is John, and today we're focusing on the teaching of Euclidean geometry as part of the curriculum for mathematics. We recognize that over the last little while, mathematics in the NCS curriculum, the teaching of Euclidean geometry hasn't been a compulsory section. It's been an optional section. There are a number of reasons why that decision was taken. But in review, on the basis of the CAPS document, the inclusion of Euclidean geometry has been motivated, and it's there for grade 10s, 11s, and 12s. So no longer will we have a situation in a couple of years' time where learners that are doing mathematics will have an option to not do geometry. They won't have an extra or additional paper like is currently the case with paper 3. Now, those topics are important, and we do need to recognize their importance and their validity. But before we get into the debate about why we should have Euclidean geometry, let's go and have a look at what the CAPS document is telling us in terms of grade 10 particularly. So I'm going to just take a content checklist, and let's go and have a look at what the CAPS document is saying. So in the CAPS document, and I haven't got the exact page number, looking for that, there is a section where it breaks down across the 3 different grades the ideas that are associated with a particular topic. So here I have in front of me the section on Euclidean geometry and measurement, and I'd like to show you the progression of that. If we have a look, we'll have over here Euclidean geometry. This is for grade 10, and it looks like my machine has frozen on that particular page, but I'll just quickly go through it. It talks about basically earlier work, investigating line segments and triangles, properties of quadrilaterals, and then solving problems about surface areas and problems related to that. Now, in grade 11, there's a more rigorous approach, and it builds up in grade 12. If I can just quickly highlight over here, proofs that were established in earlier grades, the requirements of proofs of riders as well, with circle geometry coming into grade 11. Now, remember, that's for 2013 grade 11 and 2014 grade 12. So we don't have to panic our current grade 11s and grade 12s. We're focusing specifically on grade 10. But what I wanted to do by showing you this page is to show that it definitely builds from grade 9 through to grade 10, through to grade 11 and 12. Let's have a look at those in a little bit more detail. So the content checklist starts out by saying we've got to take a look at certain revision topics. So under the content checklist, it speaks about revising lines and angles. Now, there might, in some instances, have been a phasing out of geometry in grade 9. So it's really important that even though CAPS doesn't apply to grade 9 at the moment, that teachers who are teaching grade 9 in your school recognize that there's a foundation level that's required in order to progress in grade 10. And so this year, when you start to teach Euclidean geometry to your grade 10s, don't be surprised if many of the basics that you would have expected to be in place may not be in place. Some teachers might have thought, well, it's not being examined in grade 10, 11, and 12, so we're not going to emphasize it as much. We need to cut our syllabus. It's very full, so we won't emphasize that too much. So therefore, it's really important for us, this group of grade 10s, to nurture them in understanding of the basic concepts of properties of a line, properties of an angle, and make sure that they've got those really well in place. The other aspect that is revision is the difference between similarity and congruency. And this is emphasized, and it is critically important because it's going to build on in grade 11 and 12. Congruency and proving two triangles congruent is a classic Euclidean geometry technique. And we need to remember that. We need to not just teach the learners the form, but the reasoning and the way of thinking. And I think that's really important. Just to clarify here, that if we had two triangles that are equiangular, they have the same angles, and I'll notate it with dots and crosses. Those two triangles have the same angles. I've just put another symbol in this one, a star. Put a star in that one. Not really necessary. If two angles are the same, the third one will be the same as well. These two triangles that I've drawn, not very well, but I've drawn them in any case, they have the same angles. We say they're similar. They are different sizes. Notice there are different sizes. This one is small and this one is much larger. This is bigger, it's larger, has a different area. But what we would be able to say is not only are the angles all the same, but there is a ratio, a defined ratio between the sides. And so the ratio of the sides are in proportion. And so if we had to take a look at numbering these or labeling them, and we call that one A, B, C, and we call this one D, E, F, what we would recognize is that this side, A, B, is directly opposite that angle marked with an X, as is DE, which is marked with an X. And we'll be able to say that the ratio of AB over DE is going to be a certain ratio that is going to be the same as another two pairs of sides. And you can draw up these ratios in terms of each other. And so we'd recognize that this is an important definition of similarity, and as such is referred to in the CAPS document. On the other hand, congruency doesn't mean that they're similar, doesn't just mean that they are have the same size of angles, but means really that the triangles are identical. That there is nothing about one triangle compared to the other that is any different. They have the same size of sides, they have the same angles. And there's a process about proving whether two triangles are congruent. And at this point, I don't think it would be you would be misplaced to go over how we could show that triangles are exactly the same, are congruent. There being three main ways of doing that, and I'm sure that you'll be able to investigate those with your learners in a particular way. Now, the next point that comes out in the CAPS document tells us that we need to perform some sort of investigation. And it's about an investigation of lines joining the midpoints of two sides of a triangle. This, in classic terms, is known as the midpoint theorem. And there are a whole lot of opportunities to investigate and to explore the properties of the size of the angle, the area, the nature of the lines, and get some relationships going as far as those are concerned. Investigations should be encouraged, and the document, the CAPS document, does that. Now, that just leads us into quadrilaterals as the next section. But before I go on, I want to just remind you from the CAPS document that the proof of the midpoint theorem, as it's called, is specifically required for grade 12. So there is an emphasis in grade 12 that we do need to have this pre-knowledge from grade 10 that feeds through. So please take that particular investigation, a practical investigation, as very important. When we get to grade 12, when we get to our next topic of quadrilaterals, we get to something that is more formal. And so I want to just mention what we're required to do. We're required to define different quadrilaterals, and that means we need to classify them. Classification. We need to look at their properties. And we need to then start to have some ideas, put forward some conjectures that we can then go through a process of proving. And proving of conjectures is not a straightforward task, but it is a critical task as part of Euclidean geometry. Euclidean geometry is in fact not just about shapes, it's not just about measurements, but it's a process of reasoning and thinking. And that is really what we're trying to teach our learners. When we talk about a conjecture, we're talking about an idea that we can go through a set of processes, a set of steps to either show that the conjecture is valid and it's true for all of those particular examples, all of that class of examples, or it might not be true. And so we'll need to find other things about it, come up with different conjectures, different statements that we can then say, are these true or aren't they? And the reasoning involved in that is of a particular kind. Now, the layout and the format of that traditionally has been done very systematically. There has been a move away from that formal reasoning, and I believe that's not a bad thing. We can get story proofs. We can get that they're not written very formally. We do want to get our learners to the point where they are writing formal proof, but there is a lot of research saying if you can get your learners to express what they're thinking and give a reason for it in a story proof, that might just be have a logical sequence to it. That would be a good starting point to teach them the process of formal proof. It's not something they're going to, as 15-year-olds, be able to dive into straight away. We recognize that this is a higher order thinking, and it needs time and it needs practice. And even when learners get to grade 12 level, many learners don't really understand what the essence of formal proof is, and they might well be confused. So it's a skill that needs to be developed. It needs to be started very slowly, and it needs to be introduced carefully so that learners don't get lost on the way. One of the things that the literature tells us in the research is that learners very easily build up a barrier to learning about geometry. And we don't want that to be the case. We want to make it engaging. We want to make it practical. We want to encourage them to start thinking like mathematicians. And geometry is the opportunity, Euclidean geometry in particular, is the opportunity for them to get that framework and that scaffolding so that they can reason and reason logically. Okay, so having said that, I think we've covered the content that's required specifically for Euclidean geometry. There are other sections within the CAPS document that are referred to together with Euclidean geometry dealing with measurement, but we are not going to deal with those today. So the measurement of volume and surface area and the calculations thereof, we'll just leave that for another time. But specifically let's think about discussing the teaching of Euclidean geometry. Now we have an idea of what we need to teach. We recognize that we're going to need to teach more or less the stuff that we've taught before. Before the NCS was introduced under the NATED 500, there were topics on quadrilaterals, there were topics on triangles, the midpoint theorem was included. And if we go back a number of years, you'll recognize that there's no new concepts really, but they are the order has changed. The position of circle geometry, for example, has moved from grade 12 to grade 11. But that's not for this discussion. We're dealing specifically with grade 10 at the moment. So how are we going to rationalize and approach the teaching of this, bearing in mind that there is going to need to be a fair amount of revision? And the teaching approaches we'll come to in a little while. But before we get there, let's just have a short discussion on why teach Euclidean geometry. What's the reason for it? Well, there are historical reasons. Historical reasons. And perhaps that's the most important place to start. If we think about the way that geometry has evolved or has developed over time, and the thinking behind the nature of maths and the nature of science to a certain extent, one needs to recognize that Euclidean geometry has very deep historical roots. In fact, we're talking about the origins of Euclidean geometry being about 3000 BC. Euclid was an Egyptian, so he was an African, and in that sense it's something to celebrate. What he put in place in his writing called the Elements was a set of a framework for reasoning and for thinking that has influenced Western civilization and Western philosophy throughout the Middle Ages, the Renaissance, and even beyond. And so what we need to recognize is that Euclidean geometry as a way of thinking is extremely powerful. And the reason for that is that when we look at logic and thinking, there are really two forms of thinking. There are two ways of thinking. And the one as known as inductive reasoning, and the second is known as deductive. Now, in terms of what Euclidean geometry tries to do, it doesn't take a particular example and then try and from the given information find the solution. That would be an inductive approach. If we, for example, are given a sequence and we're asked to find the next three numbers of the sequence, you can look inside the pattern, recognize that if the rules for finding the first three or four numbers were the same, then by implication, using that as a model, you'd be able to get the next three. And so that would be inductive reasoning. It would follow on as a consequence of what you have already been given. Deductive reasoning starts with a clear process of recognizing that we've got some generally held truths and we move from 1 to 2, and if 1 is telling us something and 2 is telling us something, we combine them to make the final point of 3. So we deduce, given various values, various principles, various ideas, definitions, and we work from those definitions to find the final conclusion. And so it's a very systematic way of reasoning. I want to just show you very briefly something about Euclid. And there are many opportunities to talk about Euclid, and there are many issues around Euclid. This is an article that, or a website that particularly just gives us some idea about the nature of Euclid's elements. Shows you that this is a very old book, and it's been translated as many times as some of the very old literature has been. And there we go from the initial precepts, the organizing of Euclid was done in terms of some basic ideas to start with, some definitions, and once we got those definitions, we then got some commonly held ideas which were known as axioms. We put those together, and then out of those we reason and we have clues to say because of this, because of 1, 2, and 3, we can then say that whatever the principle is, we can deduce the idea using those initial definitions. And so it is an unusual way of reasoning. It's not a common way of reasoning, but it is used in many fields of modern life. Even today, we have a legal argument that is basically based on deductive reasoning. You have people solving crimes based on deductive reasoning. You have mathematical arguments at much higher level than school based on deductive reasoning. And so the power of deductive reasoning and the power of logic is extremely important. Now, we're going to talk a little bit more about the reality of Euclidean geometry, because it's not just because it has this historical value, but it definitely has the idea of logic and building up logical thought. And it's about training learners to have that logical thought. But in particular, it's applied to something that is relevant to us. Around us all the time is the idea of geometrical shapes and the properties of these shapes that affect our lives. So there is design that's related to shapes that can include architecture. It can include simple graphics. And these are part of our everyday lives. It can also include things related to marketing, as we think about boxes and containers that people would find. And so the world is a world full of shapes. And what we want to encourage learners is to explore this world of space and shape, and for them to get an appreciation for the shapes that are in the real world, and to get an idea of engineering around those, to get the structures around those, so that they are familiar with recognizing the properties of different shapes. But what we need to recognize is that Euclidean geometry deals with a particular, and particularly at school level, deals with two-dimensional shapes. They're flat, they're not on a curved surface, but they are two-dimensional. And learners need to engage with these to have an appreciation of what's going on. And they can relate from the studies in Euclidean geometry to what's happening in the real world when they link Euclidean geometry to measurement. Okay, I think that we've got some concepts going and some discussion. Maybe you don't agree with the reason for teaching Euclidean geometry, but I think it's really important to give learners the opportunity to sharpen the focus on reasoning. And above all things, that's the important reason. We're going to go to a short break. After the break, we'll have a look at some teaching approaches that you might want to take, you might want to consider, and then we'll look at some resources that you might want to implement and integrate into your classroom practice. We'll see you after the break. Colleagues, welcome back. This is Learn Extra Teacher Talk, and our focus today is on the teaching of Euclidean geometry. We've already had a look at the topics in the CAPS document. Recognize that this is an important section, that learners need to be reminded about lines and angles. They need to be reminded about triangles. They need to be reminded about congruency and similarity, and then they'll move into quadrilaterals and the properties of the quadrilaterals, defining and classifying quadrilaterals and having a look at those. Now, in terms of Euclidean geometry, why we teach it and why the universities, I think, were particularly concerned about engineers and scientists not being the ones that were coming into the program at first year level, and many learners did not have paper 3. And so they were disadvantaged to a certain extent because they hadn't delved into the reasoning and the practical logic that's required in solving geometrical problems. Now, I know that it's contextualized within the topic of shape and space, but it really is a reasoning process. And that's one of the historical reasons when we look at Euclid and we look at the Elements, the book that he wrote, that has been revised and translated probably as many times as the Bible has. It's one of the most amazing books from antiquity that we've got available to us. And it's got this deep thinking that has framed our way of thinking, or has framed Western ways of thinking. And the interesting thing, of course, is that it comes from Africa. So in many ways, this is an indigenous knowledge system, something that we can instill a pride in our learners, that there is a tremendous amount of rich thought that comes from Euclidean geometry. So allow them to appreciate that by putting in together a system of thinking, we've been able to develop a whole range of other information and other ideas that have led into real-world applications. So when your learners ask you, why am I teaching, why are we learning this? It's about teaching you to think clearly, and it's also teaching you about the world of geometry, the world of shape and space. And the world out there is enormously filled with shape and space, and our lives depend on it. So how are we going to approach it? What are the different ways of approaching it? Now, I might not have all of the ways, but I want to just discuss with you a couple of suggestions. Some of these come from literature, and some of them are just practical things that I've observed teachers teaching in their classroom. So the first thing that we need to recognize is that lots of learners have a fear of geometry, and so we need to make it hands-on. And this means that there is a practical side to it. Now, I know the purists will probably say, but we should be reasoning in an abstract way. For grade 10, I don't believe that that's necessarily true. Their level of development doesn't allow the majority of grade 10, 15 and 16-year-olds to level at a formal abstract level. And so we need to assist them. We need to give them space to explore. And that means taking cutouts, using a protractor. So it's protractor, a pair of compasses, and a ruler even. And making sure that learners can start to explore with direction some postulates. Now, postulates are ideas that are similar to conjectures, where somebody comes up with an idea, and we would want to ask, is this really true? Is it true that to make a triangle, one side has to be larger than the sum of the other two? So for a particular triangle, if we have a triangle ABC, is it true that if AB is the longest side, then AB, the length of AB, must be greater than BC and CA? Is that really true, or is it not? Well, here's an interesting thing. I'm not sure at this stage how we're going to find out. Well, one of the things that we need to recognize is that you might find many examples that this is true for, but you only need one example to show that this is not true. And so in terms of logic and in terms of proof, how are you going to prove something? One wrong or counter counter example will disprove a conjecture or will disprove is sufficient. You just have to find one exception to the rule, and the rule can no longer stand. One counterexample. It doesn't matter how many true examples there are, but one counterexample will disprove it. And so I think it's really important that learners do some of these thinking steps in a practical way. And they could use simple apparatus like protractors and rulers and so on. The other way or the other approach is starting with something that they know. And we could actually say to them, well, let's list the axioms or the knowledge, the prior knowledge. We want to get hold of our prior, sorry, that's a spelling mistake there, our prior knowledge, the facts that we know that are true. And some of these will be what we will recognize as axioms, and definitions. And the amazing thing about Euclid's work is that he had very few axiomatic or simple statements or definitions that started his whole construction of proving different ideas about shapes. And so these we can give to learners as formal things, statements, and out of those we can start to say, well, what does this mean about angles? What does this mean about triangles? And so we start to get a series of conjectures and proofs that we try and reason out. It's an argument. Now, the argument could be formed in terms of a group work exercise. Can you show that, for example, the angles of the external angle of a triangle is equal to the internal opposite one? How can we show it? We need to find some ways of showing it. Getting discussion and argument is really important in terms of this reasoning process. I want to mention a third thing that is another approach that is found in the literature. And the third process is to say, well, let's include some ideas about transformations. And it builds logically, because we can say, well, for example, I'll just give you one example. We know that if we have a triangle, let's call this an isosceles triangle, meaning that those two angles are equal to each other and the opposite sides are equal to each other. This isosceles triangle can then be manipulated and copied to get a whole range of patterns. And so if I were to take this particular triangle, I just want to select it and see if I can copy it, and I'll do this, put it onto that particular function, and let's see if I can make another one of them. And there I go. It didn't give me everything, but I think I can pull another one, and so on, and so on. And I can get a pattern going. This has been done many times, and you might have seen it before. But if I just translate, I'm just sliding these patterns together, and I'm getting a new pattern to form in this way. Now, I'm going to say the properties of this row of patterns is that all of those angles are the same. This angle is the same as that angle. That one is the same as that one. That one's the same as that one, and so on. I hope you can see that we've got a whole lot of information that's put down here. But what's interesting is that as we've put them, we can start to look at some processes. We can start to look at some ideas here. We look at that particular point that I've circled. It's possible for us to recognize that if we take a triangle, that we could even fit one of them into the top over there. It would be exactly the same. Now, this angle here, I'm going to mark with an X, and that angle there would be exactly the same. We would be able to show without too much difficulty that those are printed from the same masterpiece. You could have stamped them out. And so what are we beginning to see? That in this case, the angles that are vertically opposite each other are the same. We can also show that, that these angles, angle 1, angle 2, and angle 3, form on a straight line. They would add up to 180 degrees, and they're angles that are the angles of the triangle. And so here's a way of using transformations to prove certain geometrical ideas. Right, I want to move on to our next idea. These are just some approaches that you'll find in literature, and you might have some others. There might be a number of others, but I want to show you some resources that might be helpful in teaching geometry as well. And one of the things that I want to mention here is the use of computer technology. And the idea that I want to mention to you, the program is a free web download. You don't have to pay for the license, is GeoGebra. Just have a quick look at this program here. I've redrawn a triangle. And what we've been able to do is on this triangle, let me select it, and hopefully it's going to pull in very quickly as we're running a little out of time. It's able to show you the angles, and you're able to manipulate the diagram so that as you change the shape of the triangle, the angles change. Let me see if I can get it. There it is. Have a look at that. As I'm changing the shape of the triangle, just move it in, and you can see that the angles change correspondingly. It doesn't matter what size it is. And what you can also notice is angle A and angle D are always the same, independent of the shape of the triangle. So this program, which is really quite useful for teaching Euclidean geometry, is one of those resources that I would suggest you have a look at. Now, the last one that I'm just going to quickly mention, and I haven't got a lot of time, is again to refer you to the Mindset website and to say to you there are a whole range of videos in grade 10 and 11 that are relevant for the teaching of grade 11. These are videos that go through the process of teaching Euclidean geometry in a very systematic and a very careful way. So have a look at those videos, and you might also want to even download the lesson notes. This is a lesson note on deductive reasoning as an example, and it gives you a particular exercise that shows very clearly the difference between inductive and deductive reasonings. Now, I hope that gives you an overview for some of the resources. You might say to me, but hold on, I'm not very computer literate. Is there somewhere that I can learn and I can get some more information? Well, if you go to GeoGebra, the website is very easy to remember. It's simply this name, geogebra.org. And if you forget it, you can Bing it or Google it, and you can get to geogebra.org. And within geogebra.org, you can download the program, but you can also download some lesson ideas. What I've downloaded here is an instruction manual on how to use GeoGebra. And so I just want to show you that it's got a whole range of topics for using GeoGebra, and that includes constructions, algebraic inputs, It also includes some very simple transformations as well. And so have a look at those. There are fora, there are places you can ask questions. It's about learning together, lesson examples, lesson ideas. Some of these are even posted onto YouTube. And so I would encourage you to use as many different resources, GeoGebra being one, and the other resource that I've mentioned is the Mindset to Learn videos. There are videos and notes that will be most helpful to you. Right, guys, I know that that last bit was a rush, but I hope that you have got some idea and some ideas you can take away in terms of using different approaches to teaching geometry. It's been my pleasure to host you this afternoon. Please send me your ideas. I'd love to hear from you. From me, John, goodbye.